Hello and welcome back to Math 301 Combinatorics at CSU. Today we're going to be talking about Cayley's theorem, which is one of the most celebrated theorems in combinatorics. It's a formula for the number of distinct trees on n labeled vertices, and the formula is that it's n to the n minus 2. So as an example, let's look at three vertices. Say you have three labeled vertices, 1, 2, and 3. The formula would say that it's 3 to the 3 minus 2, which is 3 to the 1, or 3. So what are these three trees on three labeled vertices? Well, to make a tree on three vertices, you basically have to make a path. There's no other possibility. And as far as what that path is, it can go 1, 2, 3, or 2, 1, 3, or 1, 3, 2. 1, 3, 2 is not different from 2, 3, 1 because these aren't directed graphs. So those are the only possibilities here. And let's look at an example for four vertices. Then you have different types. So it will have a lot more examples. There's 4 to the 4 minus 2, or 4 squared, which is 16 possibilities. And so we'll just list a couple of them here. So certainly you can have a path labeled in any way with 1 through 4, but you can also have a tree structure that involves a vertex of degree 3 with 3 leaves coming out of it. And there, of these two types total, there's 16 when you consider all possible relabelings. But then it just gets more complicated as the numbers get bigger. And so the question is, how do we prove this? And we'll see one proof of this today. So why is it n to the n minus 2? Well, one way to approach this problem is to first try to simplify this formula, turn it into n to the n, and count something counted by n to the n, which is a little bit of a simpler formula. And the way we modify our problem to have the answer be n to the n instead is to define a rooted tree. A rooted tree is a tree along with one special vertex chosen to be the root. And the root of the tree, we usually circle the root. So there's that circled root, and you can see it looks like the tree is planted in the ground at the root if you draw the root at the bottom, and then all the branches and leaves are coming up this way. So the question is, how many labeled rooted trees do we have on 1 through n? Well, the number of rooted trees is n times the number of unrooted trees, because there's n ways to choose a root. So we have, say we assume Cayley's theorem is true, there's n to the n minus 2 possibilities of labeled trees without a root, and then we choose a root in n possible ways, and that bumps it up to n to the n minus 1 total. So the idea is we're going to do this again. We're going to multiply by n twice by choosing two roots. And this is going to be called a doubly rooted tree. So a doubly rooted tree is a tree along with two vertices chosen as the first root and the second root. So let's say we have a red root and a blue root. These red and blue vertices might be equal. So you just choose the red one in n possible ways and choose the blue one in n possible ways once you have your tree. And so altogether, how many possibilities do we have? So again, assuming Cayley's theorem is true, we would have n to the n minus 2 times n, 1 n for each choice of each root, and that brings it up to n to the n. So it suffices to prove Cayley's theorem to count the doubly rooted trees. We need to show, if we can prove that the number of doubly rooted trees on n labeled vertices is n to the n, then by dividing back by two n's, we can conclude that Cayley's theorem n to the n minus 2 is actually true. So this is our goal. Number of doubly rooted trees is n to the n. So what else is counted by n to the n? Let's find another interpretation of n to the n, a simpler one, and then find a bijection between doubly rooted trees and that interpretation. And the interpretation I want to use is that it's the number of functions from the set 1 through n to itself. No restrictions on the functions, any possible functions. So when we did sets, we mentioned functions from a set to another set, and we can draw these functions as arrows going where every point in here goes to exactly one point over here. And so to count the number of functions, for number 1, there are 4 choices as to where the arrow coming out of number 1 goes to. In this case, we chose f of 1 equals 3, but there's 4 choices for that. And there's 4 choices for f of 2, and 4 choices for f of 3, and 4 choices for f of 4. Altogether, we would get 4 to the 4th power. In general, we would get n to the nth power because there's n choices for each of f of 1, f of 2, up to f of n. So this is something that's counted by n to the n. And now we just need to match these functions up with these doubly rooted trees to show that there's also n to the n doubly rooted trees, one for each of these functions. So in order to make this bijection, we first draw the function in a different way. So given a function from 1 through n to itself, we want to draw it as a directed graph. So the nice thing about functions from a set to itself is you can kind of merge the two sets, just push them together, and make it into one diagram where you have the elements 1, 2, 3, and 4 in this case, and we just draw the arrows. So here 1 goes to 3, so we'll draw an arrow from 1 to 3 here. And then you can say, okay, 2 goes to 3, so we also draw an arrow from 2 to 3. And then we have, let's see, 3 goes to 1. There's an arrow back from 3 to 1. And 4 goes to 2. So let's draw 4 goes to 2. That's the directed graph representation of a function. Now, which directed graphs just mean a graph with direction on each of the edges, right? The arrows are pointing somewhere, and it can have loops. In fact, all paths in a directed graph of a function eventually lead to a cycle, because if you keep applying the function over and over again, eventually you'll get into a loop. And every vertex has exactly one arrow coming out of it. That's what the function condition means. And so you just get a bunch of cycles with a bunch of arrows leading into the cycles. So that's what a function looks like as a directed graph. Here's a more complicated example. Here's a function that we've drawn as a directed graph where you can see things like 3 maps to 2 and 8 maps to 2, and then 2 maps to 9, which maps back to 2, which maps to 9, which maps back to 2. So you get into these cycles. And if I wanted to write this down as an actual function, let's just see where everything goes. So f of 1 is 7 because we have an arrow from 1 to 7. F of 2, we said, is 9. F of 3 is 2. F of 4 is 7. F of 5 is 4. F of 6 is itself. So you can have, an element mapped to itself, so we can have a self loop here in this type of directed graph. And f of 7 is 5, and f of 8 is 2, and f of 9 is 2. So we could have described the function with all of this data, but it's actually somewhat nicer and more visual to draw it as this directed graph. And we can use these directed graph drawings to then make a tree to make this correspondence with the doubly rooted trees. Okay, so remember again, to prove Cayley's theorem, we need a bijection from these functions, which we're drawing as directed graphs, to the doubly rooted trees on 1 through n. We need a bijection, which is a one-to-one correspondence, exactly matching up the functions with the doubly rooted trees. So how do we go from a function to a doubly rooted tree? Well, again, first we write this as a directed graph. So here's the function that we wrote above. And now the trick here is first you consider the least element of every cycle. So we first want to look at these cycles because the cycles are really the things that don't look like trees, right? Trees don't have cycles. We want to make them not cycles anymore. So we're going to first put them in an order. You take the least element of each cycle. So 2 is the least element of the 2 and 9 cycle. 4 is the least element of this cycle, and 6 is the least element of its own cycle. And so look at those smallest elements, 2, 4, and 6, and you order them by the decreasing order of their least element. So these purple numbers, 4, 6, and 2, we're going to order them from biggest to least, 6, 4, 2. And we're going to order these cycles in that order. So we're going to just draw this 6 over at the left. We're going to move that, we're going to organize the graph that way so that we think of that this cycle is the first one, and this cycle is the second one, this cycle is the third one. So here we're going to just watch these be reordered. It's the beauty of notability on an iPad. Okay, so let's order them like this and line them all up where you start, and each cycle is going to start with the smallest element, and then you're going to list the other elements in order after that in the cycle. Okay, so now that we've organized that like that, we're going to turn the ordered cycles into a big path where you just connect all the cycles with one big path from left to right in the way that we ordered them, and make them just one path, no order, no directed arrows or anything like that. And also erase the arrows on all the other edges, just make them undirected edges. So this forms a tree, and we choose the first and last element of that path of cycles as the roots. So again, this 6 is coming from that 6 cycle, the one cycle that we had, 6 mapping to itself. Then 4, 7, and 5 was that second cycle, and 2 and 9 was that third cycle. We just connected them all up and made it the first and the last be the 2 roots of the tree. So this produces a doubly rooted tree in a unique way. And how do we show that this way of corresponding these objects is a bijection? Well, to show something is a bijection, you have to show it has an inverse, which means we need to show we can reverse this process. Starting with this tree, pretending we didn't know what that directed graph was, can we reconstruct what that directed graph was? Well, yes, you start with the first root and you want to make a cycle. Well, what you do is you follow this path towards the blue root until we reach a number s less than r. So if r is 6, that's our first number. We keep going until we reach something less than 6. Oh, wow, we reached it after one step. So when you get to a number less than the one that you're looking at right now, then you stop and you loop back around to where you started searching. So we'll make a cycle from R to, going towards everything before S and then looping back around. In this case, it's just one vertex. But then you continue this process starting from S. So we make a cycle from R to just before S and back, and then we continue with S as our new R. So we search from here, we go along towards the 9. So from 4 to 7 to 5. Oh no, 2 is less than 4. So there's another number less than the current number we're looking at, which is 4 in this case. Let's call that T. We don't want to include 2 in our cycle, because otherwise that would be the least element of the cycle. We want 4 to be the least element of the cycle. So we just make it wrap around back to 4. And then we pick up 2 again and we search to 9, and that's not less than 2. So we include 9 and we wrap back to 2. And so you see we've actually recreated the cycles that we forgot about. So choosing this ordering really does allow us to recreate the function that we started with in the first place. And that means there's this one-to-one correspondence. And so there are n to the n doubly rooted trees on n labeled vertices. So one thing I want to point out is there was one fact about trees that I was implicitly using in the proof above, and it looked visually obvious, but it's not actually the easiest thing to prove. So the fact about trees that I used is if you have two vertices, v and w, in any tree, then there's a unique path between v and w. There's only one way to get from v to w. And for the proof, well, trees are connected. If it's not connected, it's called a forest, right? If you have multiple trees. So trees are connected. So there is a path between any two vertices in any connected graph. So there's at least one path between v and w. And now we'll do a proof by contradiction. Assume for contradiction that there's two paths from v to w. Let's say a black path and a blue path, but all of these are ordinary edges on the graph. And we're going to show a contradiction that it's actually not a tree. So if there's two paths, then if they're different, then at some point they must, as you go along, maybe they're the same to start, but at some point the black and blue edges split. And you take the first point at which it diverges, and then you keep following the black path until you get to a point at which the first point at which the blue remerges with that black edge. And what that means is that we have a non-trivial cycle in our tree that doesn't involve, just going forward and back. And so, in other words, you'll always be able to form a cycle if you have two distinct paths from v to w. And so that's a contradiction because we assumed our graph was a tree. And a tree is defined as something that has no cycles. So that's why we use that to make that unique path from the red to the blue vertex in Cayley's theorem. And that unique path always exists, and it's always just the only path we can have. So now you try to explore this proof of Cayley's theorem by drawing the doubly rooted tree corresponding to the function that's drawn as this directed graph shown below. And I just realized I wrote digraph. That's short for directed graph. So that's all for today, and we'll see you next time.